the very first thing we are discussing today is the GRE tunnels. And when we talk of GRE tunnels are something which encapsulates the original packet with a new header having a different source and destination IP addresses. GRE stands for Generic Routing Encapsulation. It's a method of tunneling which do not support any sort of security. So isn't something that should be used on a public infra, but is a good option to be used inside the network or sometimes over the private connectivity. So when you want to configure a tunnel, like a point-to-point connection between two remote devices, you can go for a GRE tunnel. Now, how does that work? Let's see. Let's say you have a headquarter branch and you have a site number 1. They both connect to each other via some third router, which we will assume as the ISP. Now, I don't want to send my traffic via this ISP. Rather, I want to create a tunnel between my headquarter and my site 1. This is going to be my GRE tunnel, right? Both the routers are connected to the internet, and we can use this topology to simulate how two routers can connect together via the tunnel instead of using the underlay. What is underlay? Underlay is basically the physical connectivity that you have. Overlay is the virtual tunnel that we have created. So this connection here is known as underlay connectivity, and this tunnel that we are establishing would be known as overlay connectivity. But like I mentioned before, in the actual world, we do not use GRE at all with the internet because of its inability to uh, secure any kind of encapsulation. It's highly insecure. It just does the job of wrapping the packet with a new header. That's it. Other than that, it is not secure. So we gotta use IPsec for such uh, implementations in the actual worlds. But yeah, as of now, let's explore this one of the option of tunneling with the GRE configurations. I'll share my screen and let's see how the configurations work for GRE. We have this topology here, the way we discussed in the notepad. I'll start these devices. Let the devices come up, then we'll get to the configuration part. We have these 3 routers, which we are going to configure with the GRE tunnel and see how we can encapsulate the packet and can directly send it through the point-to-point connection that we established between the router number 1 and the router number 3. We are assuming that router 2 here is the ISP router. So very first thing that I'll do is I'll put the basic IP configuration. Let's go to the router number 1. Enable config T hostname R1. On interface G00, I will set the IP as 10.1.2.1/24. No shutdown, exit, and then I'll create a loopback 1, which will have the IP 172.16.1.1/24, and you'll say this represents local area network. Exit. Then I'll go to the next router, router number 2, where I'll have a very basic, simple IP config. On the GI00, we'll set the IP as 10.1.2.2/24. No shut, exit. And on GI01, 10.2.3.2/24. GI01, no shut, exit. On the router 3 also, I will set the IP configs on GI00, as well as I will add the loopback interface. So gig00 IP address 10.2.3.3/24. and a loopback 1 with the IP as 172.16.2.1/24. Description representing LAN. After this, we need to put the basic static route configuration for bringing up the underlay connectivity. Always remember that for creating any sort of overlay connectivity, the first thing that you require is the underlay connectivity. So I will go to the router number 1 and router number 3, and I will put a default route on both the networks, on both the routers, or the ISP router, 10.1.2.2, and then on R3 also IP route 10.2.3.2. On the middle router, which is my ISP router, I will have to put static routes for the loopbacks. 172.16.1.0/24, 10.1.2.1, and 172.16.2.0/24, 10.2.3.3. After this, I can go and check my reachability. I'll try to ping 172.16.2.1 and I'm getting the replies. If I trace my route to 172.16.2.1, so what is the path we are taking? We are simply taking the underlay connectivity, which is via the router number 2, right? I'm reaching the destination, but by using the underlay connectivity only. Okay, so we can see that R1 tried to ping the destination, and what path are we taking? We took the underlay path, which is via the router number 2, right? But I don't want that. I want my GRE tunnel to get into picture and take the traffic directly to the destination, for which I will configure a tunnel interface on my router number 1. Let's see how that works. I'll create a tunnel interface 0, interface tunnel 0, and I'll set an IP address on it as 200.10.1.1/24. Along with that, we have to specify the source and destination of the tunnel. So tunnel source, that's going to be gig00 of my router, and tunnel destination will be gig00 of R3, correct? So we will have to put the IP of gig00 of R3. That's all what you need to do. No shut, exit. Similarly, I will go to R3 and I will configure the tunnel interface. Interface tunnel 0 IP address 210.1.2/24. Tunnel source gig00, tunnel destination IP of gig00 of R1. So 10.1.2.1, no shut, exit. Now I will go on to these routers and I will tell them to route the traffic through the tunnel interface. So the IP route for reaching 172.16.2.0 should be sent via the exit interface tunnel 0. Likewise, on R3, I will go and say if you need to send some traffic to the destination network 172.16.1.0, the exit interface should be tunnel 0. And then I can again go to the router number 1. Earlier, when I tried to check the reachability, it was via the router number 2, right? 10.1.2.2. But now if I try that thing again, let's see, ping 172.16.2.2. First of all, sorry, 2.1 it is, 2.1. So the reachability is there. And if I check the path which it is taking, 172.16.2.1, you can see it is directly sending it to 210.1.2, which is the tunnel interface IP of R3. So now it's no longer using the underlay. Now it is using the overlay reachability that we have established. The next thing that we are looking at today is IPsec tunnels. Like I mentioned, GRE are not something which we can rely on for internet communication, but IPsec is something that we utilize. We all use this term called site-to-site tunnels and the VPN in the productions, right? When we are talking about that, we are actually talking about implementing IPsec only. Now, IPsec is not a particular protocol, it's a suite. When we say it's a suite, it means it's a combination of various things. Okay. It provides you a secure method of transmitting data over a public network like internet and can help you in ensuring that your data travels safely over it. The data is authenticated here, it is encrypted, and integrity is maintained. So everything which is important to be considered while you send your data over internet is something that IPsec takes care of. Now for implementing IPsec, again, first of all, you require the underlay connectivity. Then you require to set the phase one configuration, which is about setting the parameters about key exchange. Okay. So when I talk about IPsec configuration, let me open the notepad. So we can say IPsec, first of all, stands for Internet Protocol Security. And when we speak about IPsec, we can say it's a collection of rules and protocols which work together to establish a secure connection over public internet. When we speak about the features of IPsec, it takes care of three important things, like I mentioned. It takes care of authentication, takes care of integrity. Authentication means authenticating the IP packets using some password or some RSA key. Integrity means that ensuring that IP packets are not modified in the pathway. Then confidentiality, which is basically ensuring the data is encrypted. That is something which IPsec takes care of. And the key exchange is done with the help of IPsec itself. You don't need a separate protocol for that. So key exchange is also something which it does internally itself. Now, when we implement the configuration of IPsec, we break it down into two phases. The phase one is all about setting IKE parameters. What is IKE? Internet Key Exchange. In this, you create a policy, you define a policy where both the parties or both the peers decide to make an agreement. They decide to specify that what authentication algorithm they will use for the key exchange. Then along with authentication, you specify what encryption method should be used, what hashing algorithm should be used, what should be the group number. Group number defines the, we can say, complexity of the key exchange. Okay. So you specify all these things and also the lifetime, right? You specify these things in the phase one. These are about specifying how they should be using the algorithms for the key exchanges. Okay. Then phase two is about specifying how the data should be treated inside the tunnel. So the user data which travels inside the tunnel, how that should be treated. In this case also you specify basically what should be the hashing algorithm, what should be the encryption method, and so on. Now, when you configure the phase 2, there are two types that you can use. You can use a tunnel mode, which we can say two types of phase 2 implementations include tunnel mode, which is uh, encapsulating the and encapsulating the whole of the IP packet, including the header, the data, everything, right? Then you have the transport mode, which is basically encapsulating or encrypting the actual data, not the header and the IP information. So only the actual data to be transmitted is encrypted, and the header part or the IP packet information is remain untouched. Okay, so this is when you want to establish an end-to-end connectivity. So we'll look at the configuration now. We'll look at how things work, how the hashing works, how we specify the encryption, authentication, how we define all the parameters. All right. So I'm going to boot this topology and we'll test out the configurations over here. The very first thing is setting up the basic IP and routing configs. I'll take the access one by one. That's my router number 1, router number 2, and router number 3. All right, the devices are ready to be configured. Let's put the basic configurations on them. I will take the access of router number 1 first, set the IP configs over here, enable. Config T, host name R1, interface GI0/1, IP address 192.168.12.1/24. No shut exit. And then I'll create a loopback 1 with the IP address 1.1.1.1/32. This represents the LAN device. Exit. Then I will go to router 2. Here also I'll put the basic configs. Host name R2 GI00, IP address 12.2/24. No shut exit. GI01, IP address 23.2. No shut exit. We don't need any loopback here. Then lastly, my router 3. Enable config T, host name R3 GI00, IP address 23.3/24. No shut exit. Then a loopback 0 with the IP address as 3.3.3.3/32. Description representing the LAN device. Exit. The basic IP configs are done. Now the next step is setting routing. So routing, again, I'll just put on R1 and R3. The middle ISP router is something we will not touch. On R1, I will go and add the static routes for 192.168.23.0, setting my next hop as 12.2, as well as I'll put a static route for the loopback also 3.3.3.3 with the next hop as 12.2. I'll tell you the reason about adding this route, okay, later on. Similarly, I will go to router 3. I'll put the static route for 12.0 first, /24, with the next hop as 23.2. Then 1.1.1.1/32 with the next hop as 23.2. Now it's time we begin with the IPsec configuration. Like I told you, the phase one is about setting the parameters about internet key exchange. So let's do that. I will go to the router number one and I'll show you some predefined policies. There are some default policies also which have the default values defined for them for the encryption algorithm, for the hashing algorithm, for authentication, Diffie-Hellman group, and the lifetime. We will also create a policy, but we will create a custom one. So I will go into the configuration mode. I'll say crypto, ISACAM. ISACAM is the, we can say, algorithm or the protocol for managing the keys. It stands for Internet Security Association and Key Management Protocol. So that's what we use for defining the or establishing the association between two peers for the IPsec tunnels. So under the ISACAM policy, I will specify all these 5 things. So I'll say ISACAM policy number 10 and say auth. If I hit a question mark after auth, I have multiple methods of doing authentication, right? I will go for a pre-shared key method, which is basically nothing but a password. You can use RSA encryption or you can use RSA signature also for authentication. But the simpler method or the one we will utilize here in this virtual environment is the password method, which is called as pre-shared key. So I've selected the auth to be done as pre-share. Then next I'll specify the encryption. For encryption also there are 3 methods. You can use triple DES, you can use advanced encryption standard, you can use data encryption standard. So this can vary from one organization to other because they all will have their own security standards and algorithms, right? So I'm going to use DES here, or let's say AES, Advanced Encryption Standard. Yeah. After that, I'll specify how the hashing should be done. So we again have multiple options. I'll use the standard method SHA. Lastly, group. The group number defines how complicated or how strong the key is going to be. So I'm going to use the group number 14, which has the key size of 2048 bits. And lifetime by default is going to be 24 hours. That is 86,400 seconds, the maximum. Okay. We will not modify that. Exit. I'll say do show crypto ISACAM policy 10. Sorry, do show crypto ISACAM policy. And I can see the policy that we have created. Now the same standards we have to define on the peer also so that they can come to an agreement of this particular policy. I'll go to R3. I'll say crypto ISACAM policy 10. Auth to be done using pre-shared key. Encryption to be done using AES. Hashing to be done using SHA. Group should be used as group number 14 and exit. Do show crypto ISACAM policy. And yeah, there you go. We have the same standards defined on both the sides. After entering the ISACAM policy configuration, the next important thing that we got to specify is the password. Step 2 is setting the password for R1 and R3. As we have said that authentication is supposed to be done using a pre-shared key. So now it's time to set that pre-shared key. I'll go to R1 again. I'll say crypto, ISACAM key and set a password for myself. let's say Cisco@123, and specify the peer address, which is 192.168.23.3. Likewise, I will go to R3 also and set a password over there for my peer R1. So this is my R3. Here also I'll put a password, crypto, isacam, e, Cisco@123 for my peer, sorry, for the peer address 192.168.12.1. That completes my phase 1 configuration. After that, we have to specify how I want the data inside the IPsec tunnel to be treated, which is basically the phase 2. So here we can specify the tunnel mode and the transport mode, right? This is done using a transform set. Let's see. First, I'll go to the router number 1. I'll say crypto, IPsec, and select the transform set, question mark. We have to give it a name. I'll call it, let's say, VPN. And there we got to specify how the hashing should be done or how the encryption should be done using ESP. So we have multiple options. I'll say I want to go for advanced encryption standard or encryption, and then standard hashing algorithm and HMAC, which is hashed MAC. These parameters will be given to you by your organization themselves. Okay, or otherwise the security team decides how the algorithms should be selected or what ciphers are supposed to be selected. Okay, so you gotta just define them like this. And then likewise on the other side, I'll use the same transform set, crypto IPsec transform set VPN, ESP AES, and then using SHA HMAC, exit. That completes my configuration of transform set. Next step is defining the interesting traffic and using a crypto map for implementing the configurations. Okay. Interesting traffic is basically the data that you want to travel inside the VPN. So I will specify that using an access list 100 permit IP traffic from the host 1.1.1 for the destination host 3.3.3. Access list 100 permit IP traffic from the host 3.3.3 for the destination host 1.1.1. So any data which is originated from 111 and goes through 3.3.3.3 and vice versa should travel through the VPN. That's what my ACL is defining. Okay. It is necessary to define the interesting traffic because that will tell the router what data should be sent through the VPN and what should be treated normally in the unencrypted manner. After defining the ACL, I gotta specify a crypto map for setting all the parameters. So crypto map, I will call it, let's say, PyNet VPN 10, and we got to specify the method that we are using. So we are using IPsec with the isacam policy, right? There are two options. You can go for the manual key method or the isacam method. We are using the isacam policy. I set the crypto map PyNet VPN 10 with the IPsec isacam method should be set to match IP address from the ACL 100, match addresses from the ACL 100, set the peer IP as 192.168.23.3, set the transform set as VPN, exit. I will go to the interface GI01 and I will apply this crypto map on this GI interface, GI01 interface, saying crypto map PyNet underscore VPN. Exit. Likewise, on router 3, after defining the ACL, I'll create the crypto map called as PyNet underscore VPN, IPsec, isocam, enter. I'll say match IP address from the ACL 100, set the peer IP as 192.168.12.1, set the transform set as VPN. Exit. I'll go to the GI00 interface and set the crypto map PyNet VPN on it. Crypto map PyNet VPN. Exit. My tunnel is coming up, right? And then lastly, if I try to ping 3.3.3, sourcing it from loopback 1, we can see we are getting the replies. This communication itself is a proof that data is traveling through the VPN, right? Because we do not have any routing configured on R2. So if you getting the reply, that means the data is traveling through the tunnel. Okay. Otherwise, also there are commands to verify show crypto, not map, show crypto session. And there you can check if your session is up or active, up and active or not, right? So yeah, that's how the IPsec tunnel is created. Now, why do we need this route? Let's talk about that as well. Why do we need this static route 3.3.3, which sends the data to router 2? We just need it for matching the traffic in the routing table. If I'll not put this static route and I'll try to say ping 3.3.3, it will have no information in the routing table and will decide to drop the packet. Okay. Right now, when I say ping 3.3.3, sourcing it from my loopback 1, I do get my replies, right? Why? Because when I say ping 3.3.3, source it from the loopback 1, it checks the ACL, it matches the ACL, it looks into the crypto map which we have created, right? And decides to forward the traffic through the VPN that we have constructed with the peer 192.168.23.3, ensuring that my data travels through the IPsec tunnel that I have established with my peer. Right. So now the next thing we are talking about is MPLS. So we'll try to get a quick introduction to understanding how MPLS works and where do we exactly need it. So now we are talking about, again, a very important part of this particular training, which is MPLS. MPLS stands for when we speak of MPLS, MPLS stands for multi-protocol label switching. The question is that what exactly is it and how do we utilize it? If you look at this terminology, there are two terms. First term is multi-protocol. Second term is label switching. What does multi-protocol means? Let's understand that first. Multi-protocol simply means that it can work with various protocol beside IP addresses. Pretty much anything we can say. You can use it with IPv4. You can use it with IPv6. You can use it with Ethernet technology. You can use it with the obsolete frame relay as well, etc. So it is not limited to the support of IP protocol. It has the ability of working with various other transportation technologies. Then the next term is label switching. We call it label switching, multi-protocol label switching, because forwarding is done. Forwarding is done based on labels. Not by looking up the routing table. So MPLS can do anything that any other tunneling protocol can do, and it actually supports much more than that. And the basic idea of using MPLS, or the basic requirement of using MPLS, is to perform forwarding on the basis of label switching. Now the question arises, why do we need this? Okay. We'll think of an example here where we have got, let's say, two customers. We have tried this topology with our VRF configurations as well, right? What we had there was, let's say, a customer A having the site 1, customer A site 1, right? And then on the other side, we had customer A site 2. Similarly, we had another customer B, customer B site 1, and customer B site 2. Okay. And then between these two sites, we'll assume that there is ISP. What we tried previously was a very simple setup, having two routers, and the connectivity was like this, right? With the VRF light thing. But now we are assuming of a real actual scenario. So we will obviously have more than two routers, right? Assume that we have one provider edge air. Provider edge is the last router of ISP, which connects directly with the customers. Okay. Then one provider edge is here, connecting to customer A site 2. Another provider edge here, like this, and another one here. And they all connect to some provider routers. Provider routers are the core routers. Okay. Like this. In the core, we have established a mesh topology by connecting all the devices to each other, like this. Okay. Now, in any scenario, in any given situation, what we prefer or what we try to do is we try to make a BGP free ISP core. Okay, this is my ISP domain. Now, my effort or my reason of using MPLS is to make this particular core BGP free. Question is why? Right now we are talking about a very simple scenario, but a full internet routing table contains millions of routes, millions of prefixes, right? So having all these prefixes on all the routers of the ISP domain makes no sense. So what we try to do is we try to establish a connectivity between the customer A sites together with the just help of provider edge routers. Okay. Now let's not think of MPLS right now. Let's think of one possible solution that we can implement to make customer A communicate to the site 2. The one possible solution of that is an GRE tunnel. If I make a GRE tunnel between this provider edge and this provider edge, I would be directly able to transmit my customer A's traffic through the tunnel without having to make these routers learn about BGP prefixes. Make sense? Similarly, for establishing the connectivity between my customer B's site also, I can establish a GRE tunnel like this. So that's one solution, but this solution is not at all scalable. Why? Because there would be thousands of customers and I cannot have a dedicated tunnel for each and every site of each and every customer. Correct? This will again become resource hungry and would utilize a lot of my resources on the provider edge routers. So what we go for is the MPLS. Now, how does MPLS works? Let's see. We just have learned that MPLS does the label switching. That means it does not look into the routing table. So what MPLS will do? First, my customer A will give the packet to provider edge using BGP. Here we'll have BGP. From this moment of provider edge router, we will start label forwarding. Now, provider edge which will put a label on the packet and will forward it to this particular router. On the basis of label, it will forward it to the next hop. Okay. What does this helps with? This router or this router or this router or this router will never have to check the routing table because all they do is do the forwarding on the basis of labels. So only they care about the label, not the destination IP. And because they have nothing to do with the destination IP, we can ensure that this is BGP free core, as they do not have to forward it on the basis of destination IP. It doesn't matter whether they have the routes or not. All they care about is the labels, which is implemented with the help of MPLS. The only motive of this MPLS is to ensure a BGP free core, and that too when they have to forward it on the basis of IP. If let's say I talk about um, if I talk about receiving a packet from customer A that doesn't require a routing lookup, correct? Then the moment it reaches provider edge, I'm starting to work with MPLS. So again, for forwarding it to this provider router also, I do not need to check the routing table. But let's say when provider edge will receive that packet, now this is the point where the label goes off, okay? And we have to forward it on the basis of routing table. So we can say only in certain situations, provider edge devices would be looking into the prefix information. Otherwise, these devices that we have in the middle, they have nothing to do with the BGP or any sort of destination IP information. So now we know what is MPLS and where exactly do we utilize it or why do we utilize it, correct? So this can help us in faster forwarding, we can say reducing the latency and the jitter, right? MPLS can be integrated with quality of service configurations as well in a very well manner. So that is also an option to go for. Then yeah, it makes it more scalable because you don't have to worry about installing routes on, let's say 15, 20 devices. You just need it on the edge devices. So these are some of the advantages that MPLS brings in. How does this works? All of that we'll explore gradually. Tomorrow, first thing that we'll try is we'll try to implement the GRE tunnel, the first solution we were talking about, right? We will see if that can actually help us or not. And then we will switch to MPLS and observe how the forwarding happens with the help of labels. We'll talk about the LDP protocol and everything related to MPLS that we must know. And that's all for today. I have this particular topology here with me, which is a replica of what we discussed. The only difference is that we spoke about two sides of each customer Here we are looking at a simpler scenario by considering only one site for each customer. Customer A has this site number 1, which is configured in autonomous system number 10. Then customer B has site number 1 configured in AS20. Then in the middle that we have is the ISP domain, where we will try to implement a BGP free core, right? So in the session yesterday, we spoke how exactly the MPLS is used and what exactly is the need of it. Today, we are going to test the configurations of it, where very first thing that I'll try to implement is the GRE tunnels so that my core router, which is this middle P router, the provider router, this can be BGP free. Okay, that's my main goal. I want to ensure the reachability with a BGP free core. Okay, so let's see how we can achieve that. First with the help of GRE, then with the help of MPLS. The very first thing I'll do is I will start configuring these devices. I already have the basic IP configurations on them. Okay, the device is booting up. Let's wait for it. All right, this is my provider edge 1 router. If I show you the basic IP configurations on this, we have the IP configs on the physical interfaces, as well as we have a loopback 0 with the IP 2.2.2.2. After that, if I go and take the access of my next router, provider router, I'll see the similar configurations over there. You have the IPs on the physical interfaces, as well as a loopback 0 having 3.3.3.3 IP. Then we have the provider H2, show IP interface brief. There you go. Then we also have two customer edge routers, customer edge 1 and customer edge 2. Let's see how they are configured. If I take the access, show IP interface brief, I can see the IP configs. And then on the customer edge 2 also, I can go and check the IP configs. Okay. Now what I want to make here is I want to make a connectivity between customer edge 1 and the customer edge 2. And that connectivity or that reachability will be allowed only if I enable BGP on this particular ISP domain, right? Because customer edge 1 would advertise the routes to AS100 and then it has to be sent to AS20 via the AS100 so that a reachability can be established. But like I have mentioned, I want to make sure that we have a BGP free core. So for that, what we will do is we will establish a GRE tunnel between my provider edge 1 and the provider edge 2. I will create a GRE tunnel between this provider edge 1 and provider edge 2. And then through that GRE tunnel, I will establish a iBGP connection between my router number 1 or the provider edge 1 and the provider edge 2. Once I have that iBGP connection, I would be able to share the routes of AS10 and AS20 with the routers or the customer edge devices which are connected to me. Step by step, we'll move ahead and we'll understand it better how things are going to be implemented in this case. The very first thing to get started with is the OSPF configuration in the AS100. So that on top of the IGP connectivity, I can establish my GRE tunnel as well as my iBGP connection between provider edge 1 and the provider edge 2. So let's see how we can do that. I will go to provider edge 1 and configure simply the OSPF, router OSPF 10, network 192.168.23.0.0.0.255, area 0, as well as the loopback 2.2.2.2, 0.0.0, area 0. Next, I'll go to the provider router, configure OSPF here also. Config T, router OSPF 10, network 192.168.23.0.000.255, area 0. Network 192.168.34.0.000.255, area 0. As well as the loopback 3.3.3.3, 0.0.0.0, area 0. Exit. Next, I'll go to the provider edge 2 to configure OSPF there also. Config T, router OSPF 10, network 34.0, area 0, and 4.4.4.4.0.0.0, area 0. Exit. We have both the river ships up with the router number 2 as well as the router number 4. Moving ahead, I will establish eBGP connection between my provider edge and the customer edge devices. So let's see how that configuration can be done. It's going to be a very simple basic configuration. Router BGP 10, specify the neighbor IP as 192.168.12.2 with the remote autonomous system as 100, and we will advertise the network 1.1.1.1 with a mask as 255.255.255.255. Exit. Let's also configure customer edge 2 first. So I'll go to customer edge 2, configure the BGP 20, router BGP 20, specify the neighbor as 45.4 with the remote autonomous system as 100 and the network as 555.5 with a mask of /32. Then let's also put the BGP 100 configuration on provider edge 1 and provider edge 2. Router BGP 100, specify the neighbor as 192.168.12.1, remote AS 10. Exit. Simple basic configuration of specifying the neighbor. Let's see if the BGP comes up. Yeah, BGP is up. Similarly, I will go to provider edge 2, router BGP 100, specify the neighbor IP as 192.168.45.5, remote AS 20, exit. There you go. BGP is up. So far, I can say my BGP route from customer edge 1 would go to provider edge 1. And that's it. Likewise, the customer edge 2 would give the route to provider edge 2. But to exchange the route from here to here, what I need is I need BGP on provider router. But as an alternative, like we have discussed, we will establish a GRE tunnel between the provider edge 1 and provider edge 2. And then on top of that, I will create an iBGP connection between both the devices so that the routes can be exchanged. So let's do this configuration. I'll go to the provider edge 1, configure the tunnel interface tunnel 0, IP address 100.13.1.1, 100.13.1.1, 255.255.255.0. Tunnel source is going to be my loopback IP, which is 2.2.2.2. Tunnel destination is going to be the loopback of PE2, which is 4.4.4.4. Exit. Likewise, I will go to the provider edge 2 now and configure the tunnel interface over there. Interface tunnel 0, IP address 100.13.1.2, 255.255.255.0, tunnel source 4.4.4, tunnel destination 2.2.2.2. Exit. Now the GRE tunnel is also up. The last part of the configuration is IBGP configs between provider edge 1 and provider edge 2, so that the routes that we are receiving from the customer devices can be exchanged from one side to the other side. So let's configure IBGP as well. I will go to provider edge 1, router BGP 100, and specify my neighbor as 100.13.1.2 with the remote autonomous system as 100. In addition to that, we also gotta update the next hop to self so that the routes can be propagated correctly. Then on the provider edge 2 also, router BGP 100, neighbor 100.13.1.1, remote AS 100, neighbor 100.13.1.1, next hop self. End. Once this configuration is done, I can expect the route exchange over the GRE tunnel between the provider edge 1 and the provider edge 2, making the reachability up between my customer edge devices. Let's test it out. I will go to the customer edge 1 and say ping 5.5.5.5, sourcing it from the loopback 0. And we can see we are receiving the replies, correct? These replies confirm that the reachability is successfully established, even when my provider router, the middle router, has no configuration of BGP. If I say show run pipe section BGP, there is nothing, right? We haven't touched anything related to BGP on the provider router, but still the reachability is successfully established. Why? Because the GRE tunnel is there. Moving ahead, we will implement the MPLS configuration. And for that, we do not require the IBGP connectivity that we have. So this tunnel that we created is no longer required if we enable MPLS between these devices. In addition to that, like I said, if I go to my provider edge 1 and first get rid of the tunnel configs by saying no interface tunnel 0, then I'll get rid of the BGP configs that I added. So router BGP 100, no neighbor, 100.13.1.2, remote AS 100. Exit. Similarly, I will go to the provider edge 2 and I'll delete the configuration of GRE as well as the BGP addition that we made. Enable config T, no interface tunnel 0, router BGP 100, no neighbor, 100.13.1.1, remote AS 100. Exit. Now, if after that I go and try to ping my customer edge 2 from the customer edge 1, it's pretty obvious that I will not get any replies. Let's see. Source it from loopback 0. We will not get any replies because it was the tunnel which was helping me connect to the two of these remote devices, right? What else I can use here is the configuration of MPLS. I can enable MPLS and can let these devices of ISP do label switching. That will help me in avoiding the BGP configuration on the core router, right? And would also help me to avoid the hassle of creating all the GRE tunnels. So we discussed this yesterday also, why GRE is not the scalable solution. It won't be a good or a feasible idea to go for creating tunnels between all the different sites of customers that we have, right? So instead of GRE or instead of the configurations of BGP, what I can do is I can enable MPLS. How do we enable MPLS? Let's understand. I need to go to the interface which participates in the ISP core or the ISP domain. And there I need to enable MPLS one by one. So for the provider edge one, we only have one interface, which is GI01. I'll go to that interface and I will run the command MPLS IP. Then I will go to the provider router. There are two interfaces, interface GI00 and GI01. I will select both of them. Interface range GI00 to 1. I'll select both of them and I will run the command MPLS IP. Exit. You can see the neighborship is coming up between the router 2 and the provider router, the router 3, right? Likewise, I will go to provider edge 2. I will go to interface GI00 and I'll execute the command MPLS IP. Exit. After entering these commands, I will go to customer edge 1 again and I will try to ping the destination. And you'll see the magic here that I will start getting the replies soon. Okay, my bad. I missed on one step of the configuration. We have added the MPLS successfully, but BGP is still required, right? Between provider edge 1 and provider edge 2, I would need an iBGP configuration so that the routes of this customer can be exchanged with the routes of this customer. That part of configuration is missing. So let's do that. Earlier, we had the iBGP configuration over the GRE tunnel, but now we will build the connectivity simply using the loopback addresses. So router BGP 100, neighbor, the loopback of my provider H2, 4.4.4.4, remote AS 100. Neighbor 4.4.4.4, update source loopback 0, neighbor 4.4.4.4, next hop self. Exit. Similarly, I will go to provider H2, router BGP 100, neighbor 2.2.2, remote AS 100, neighbor 2.2.2.2, update source loopback 0, neighbor 2.2.2, next hop self. Once that is done, I will go back to customer edge 1. I will check my routing table and I haven't received the route yet. Let's wait for it. Show IP BGP. Show IP BGP summary. We are receiving 0 prefix as of now. There you go. We got one prefix. If I check my routing table, I will see 5.5.5.5. And now if I try to ping 5555, sourcing the traffic from loopback 0, I do get my replies. Even when, again, there is no configuration of BGP on my provider router. But what did I configure? I enabled the MPLS on the interfaces. The configurations are pretty much simple. You got to get into the interface, type MPLS IP on all the ISP participating routers. Then finally, we have created an iBGP connection between my provider edge 1 and my provider edge 2 to exchange the BGP routes. Okay, I can see you guys have done the configurations. Now it's time to understand how things are actually working. We enabled the MPLS and suddenly the traffic was again passing through the routers. But that doesn't explain what exactly is MPLS doing here for making something like this possible, right? So let's get a little into the details and try understanding what exactly are the labels which are being used here between the devices and how everything is being done. So for getting more into the concepts and understanding the label better, I will share my other screen and we'll get back to the notepad. So we discussed yesterday that MPLS contains two terminologies, multi-protocol, which means it works beyond the simple IP protocol, as well as label switching. That means the forwarding is done based on label, not by looking up the routing table. Now, what exactly is the protocol that's working between these devices to make the exchange of label possible? Let's talk about that now. So the protocol which automatically generates the label and exchanges the labels between the devices is called as LDP. LDP stands for Label Distribution Protocol. Each router will generate some labels locally, and these generated labels are advertised to each other using the protocol LDP. LDP is a standard protocol which was created later on. The very first protocol which was created to do this job was called as TDP. TDP stands for Tag Distribution Protocol. This was a Cisco proprietary protocol. This was Cisco proprietary, and later on the standard protocol was released called as LDP. Okay. Like many other protocols, LDP also establishes neighborship. We can say LDP establishes neighborship between the MPLS enabled routers. This neighborship is established with the help of a multicast hello packet, which is sent out by the routers. So initially we can say the routers first exchange UDP multicast hello packets to discover the other neighbors. Once two routers discover each other, they build the neighborship using TCP connection. So after discovering each other through multicast, we can say once the routers discover each other, they build the neighbor adjacency using a TCP connection. Clear, guys? The hello packets are sent to the multicast address 224.0.0.2 using UDP port 646. That's the default port used by MPLS. Each router is identified using a unique ID which is called as LSR ID. LSR stands for Label Switch Router. So a router which you enable with MPLS, you can call it as Label Switch Router, and the ID through which you identify it is the LSR ID. Now LSR ID is exactly like the router ID of OSPF. So by default, it will select the highest IP address on a loopback interface as its LSR ID. And if you don't have any loopback, then the highest IP of physical interface is selected as LSR ID. Okay. The neighborship will only come up if reachability is there. Like in the routing protocols also, the very first step is that you should have a reachability between the devices if you want a neighborship to get established on top of that, right? Likewise, here also we have the same concept. Now, do you guys know about control plane, data plane, management plane? So every router basically divides its roles and responsibilities into the three planes. The management plane for giving the access to the devices, the control plane for giving the for calculating things, for using the logics, and then the forwarding plane or data plane for forwarding the IP packets. So I was talking about the three planes, and we said that, yeah, every router basically manages the tasks and the responsibilities it has with the help of the three planes, right? The management plane is completely about setting up the access or giving the access to the user through the CLI or GUI. Then comes the control plane. Control plane is responsible for all the logics, all the calculations and maintaining the routing tables in the database. So assume that this is your router. So inside this router, we will have the management plane. What does management plane do? It simply gives you the access. It gives you the access to CLI or the GUI of the device. So when you access your router or your switch or any network device, you are provisioning the management plane of the device. We as a user interact with management plane. Then we take the access usually to configure protocols to enable configurations or to fetch data out of it, right? Any routing protocol that you enable on your router is taken care of by the control plane. Assume that this is my control plane. And on this control plane, let's say I am running three routing protocols, EIGRP, I'm running OSPF, and I have some static routes. Now we know that in EIGRP, the router will be maintaining a neighbor table and a topology table, right? OSPF will be maintaining a neighbor table and a database table, and static routes are directly installed, right? So all the best routes from the topology table, from the database table, they do get installed into something called as RIB. What is RIB? RIB stands for Routing Information Base. So we can say all the best routes from the topology table will get into RIB from the database table, and all the static routes would also go inside RIB. Along with all this, control plane also takes care of doing all the calculations. For instance, when I talk about EIGRP does calculate the metric, right? It calculates the feasible distance, the reported distance, it checks the feasibility condition, and then figures out who will be the successor and who will be the feasible successor. Likewise, in OSPF, we have discussed that OSPF calculates the cost, right, on the basis of the link bandwidth, and then figures out which is the best route. So it does all of that. And along with all these things, it also maintains the ARP cache. So learning the destination MAC addresses is also a responsibility of, we can say, the control plane. Finally, in the router, we get to see the forwarding plane, which we also call as data plane. And data plane has a pure, simple responsibility of forwarding data. It maintains a table on the basis of information provided by the control plane. And this table is called as fib. Just like we had rib, now we have fib. And fib stands for forwarding information base. It contains the forwarding information, how the data should be forwarded on the interfaces. Now, when you enable MPLS on this router, the control plane and the forwarding plane gets extended. In the control plane, when you enable MPLS, a new protocol is added, which is called as Label Distribution Protocol, LDP. What LDP does, LDP maintains a table called as lib. Lib stands for Label Information Base, which is nothing but a table defining what label should be used with the prefixes which we have inside, we can say the rib. So whatever rib routes we have, whatever the best routes we have, now we will put a label to them, and the details about those labels are stored inside lib, called as label information base. Make sense? And just like that, the control plane shares the information with the data plane. Data plane also extends itself and maintains another table, which is called as lfib. Now, lfib is label forwarding information base. So on the basis of label, how the data should be forwarded on different interfaces, that is what we specify using lfib. Okay. In the next chapter, we will speak about how the labels are generated, how these labels are attached, they are swapped, or they are removed when the packet travels through different devices. At every hop, there is an action taken, and then the packet is forwarded further on the basis of the attached label. So we'll see all that in action in the class tomorrow.